So today we want to take what we learned about circular motion and apply it to orbital motion. So the thing we learned yesterday is that when you have an object in motion and the force is at a right angle to that motion, that force is going to pull the object out of the straight line path and cause it to make a circular loop, a circular orbit. You'll notice that the force always points toward the center of the circle, and at any given moment the object is moving at a right angle to that force. We saw that we used Newton's second law. We found the acceleration, we plugged it in, we solved for velocity, and then possibly we solved over here for delta theta, RPMs, or time, or whatever. So the big idea we learned yesterday is that forces are required to change the direction of the object. They don't speed it up and they don't slow it down. If you remove the force, we saw that the object traveled in a straight line again. So we're going to use that along with our ideas of gravity to explain orbital motion. So some examples of orbital motion include things like the path of planets. When we are looking at exoplanets, planets around other stars, we're going to use these ideas to figure out whether or not these planets are in the habitable zone and what life would be like on those exoplanets. We'll use it to figure out orbits of moons. So if we look at Saturn, we got rings, we got moons, we got all kinds of things going around it. These formulas will let us track the motion of these different objects. Okay, if we have an object from another solar system temporarily get deflected by the sun, we can use these same formulas to try to figure out where these extrasolar visitors came from. We can use these formulas to try and determine properties of exotic stars like black holes. We can use it to help describe and model the formation of planets. We can use it when we're placing the space telescope, okay, that we launched pretty recently. If we want to try and calculate what it's going to do, we need to be able to work through these formulas. Okay, when we look at asteroid collisions, we can use these formulas to track where the Earth's going to be, where the asteroid's going to be, are they going to hit each other. We could use it to track GPS satellites, weather satellites, satellites that monitor things like the polar ice caps. We can use it to put communication satellites in the orbit and know exactly where those satellites are going to be moment to moment. We can do it for mapping satellites, spy satellites, satellites that help us evaluate what's happening after a disaster, or just our International Space Station where we have humans orbiting the Earth. These formulas will let us figure out how these satellites are going to move, where we need to put these satellites so they have certain properties. Okay, we also have satellites orbiting other planets like Mars so that we can kind of get a better feel for the geology of these other planets. So let's see how these calculations are going to work. Okay, so it's kind of a combination of things we've already learned. So if we put all the formulas we learned for the year up on one spot, here's how things are going to work. For orbits, we're going to have the force of gravity as our net force. That force of gravity is going to create an acceleration. That acceleration will let us figure out the velocity, and then that velocity will let us figure out things for the orbit, some of the properties of that orbit. All right, so this will be our flow when we're working with orbits. Okay, so the first one I'd like you to try doing is figuring out how long a year is on Earth. And I know that you already know the answer to this, and that's why we're doing this one. I'd like you to verify for yourself how good these equations actually are. So we're going to assume that the Earth travels in a perfect circle. Realize that's a slightly bad assumption. It is slightly elliptical, but it's close enough that we're going to get really good results. But realize that's the reason why our results will not be perfect. So start by finding the gravity between the Earth and the Sun. We already learned how to do this, so take out your reference sheet. Use the gravitational constant, mass of the Earth, mass of the Sun, and then the distance between them. Don't use the radius of the Sun, don't use the radius of the Earth, use the distance from the Sun to the Earth. Take that value for force gravity, plug it in here. Get your value for acceleration, plug it in here. Make sure you use the same radius here to get your velocity. Plug that in here. We're going to do one trip around the Sun, so use 6.28 as your change in theta, and solve for time. When you get your time, it's going to come out in seconds. Turn it into days and see how close you come to 365 days. Hopefully you get an answer that's pretty close to that, and that will show you that these formulas actually do predict the motion of an object that is in orbit around another object. Okay, I'd then like you to try using the same basic idea to predict the time it takes the International Space Station to go once around the Earth. Okay, so this time your two objects will be the Earth and the space station. I tell you the altitude. Remember, altitude is measured from the surface of the Earth. Make sure you turn that into meters, and make sure you add it to the radius of our planet. You're going to find the gravity on the space station. You're going to find the acceleration of the space station. You're going to find the velocity of the space station. You're going to use 6.28, and you're going to solve for the time. How much time does it take that space station to orbit the Earth once? Hopefully you'll get an answer somewhere in the ballpark of 90 minutes. It's not going to be exact, but hopefully close to 90 minutes. If you're able to do these two problems, you should be in good shape for what we do in class tomorrow.